Yeah, thank you to George. I guess since I'm the last speaker, thank you to George, and thank you. Wait, I did a mic myself up. Thank you to George, and we all look forward to the new expanded whatever it's with offices that will be here next time. And thank you to the organizers, Tim and Andrea and Stefan and Tom and Angelo and who else? I said Angelo. Okay, I said everything. Okay, thanks to all of them. Let's have another hand. Okay, I'm just gonna just give some general summary talks about what the motivation for celestial holography is, and also sort of a random list of things that have come up that look to me like they're ripe for progress in the near future. So, do we have a better one, or is this
maybe one of these is better?
okay? So motivation. Well, the zeroth order motivation is, much of theoretical physicists over the last 40 years have been occupied with developing incredible mathematical structures, string theory, ADS-CFT, and so on and so forth, which are very beautiful and compelling and tell us a lot about how quantum systems can be related to one another. But what we would like to do is, in celestial holography, is it's largely a bottom-up enterprise, and we'd like to apply. Great. We'd like to apply the last 40 plus years of work to the real world. And this seems like it might be hard, but it appears in this workshop that we actually, have tools to do this, and we might actually learn something. So, what can we try to learn? Well, we've had this again fantastic success in understanding the holographic principle, which in some sense started with the Bekenstein-Hawking formula saying that the entropy of a black hole is proportional to its area rather than its volume. It certainly didn't start in anti-de Sitter space, but it found a very precise and beautiful home in anti-de Sitter space that we have worked out in a lot of detail, and it's very compelling. But it would be a very strange indeed if holography in quantum gravity, which really originated from flat space arguments, only existed in anti-de Sitter space, yet we don't really have a concrete understanding of how it would extend to our own universe, which is, well, we thought it was flat until we thought there was no cosmological constant until 30 years ago. It's flat to a very good approximation, and we should also ultimately try to understand how it extends to de Sitter space, but that seems very hard at the present. We don't have so many tools. So we'd like to extend, and we had a very nice talk by Tadashi about extending the holographic principle to other kinds of spacetimes. So we'd like to extend it to holographic principle to flat space. And celestial holography is a proposal for a way to do that. Now, in the language I would use, celestial holography can't be wrong, because you can always take quantities, scattering amplitudes, quantum gravity scattering amplitudes, and you can rewrite them in a conformal basis, and that can be viewed as a definition of a celestial conformal field theory. And so that's sort of a tautology that it exists. It can't be wrong, but it can be useless, which is almost the same thing. So we don't really have a clear, or it might be useless. It also might not be the good way of thinking about holography in flat space. But anyway, it's a good proposal that we can think about in a concrete way. A second thing, it's kind of amazing that the standard model, general relativity, and standard model of particle physics has been around for 50 years now, experimentally tested, dozens of Nobel Prizes. We still don't know what all the symmetries, what all the non-trivial symmetries of nature are. And by non-trivial symmetries, I mean things that have conserved quantities and that we can measure, and they can make experimental predictions. For example, the memory effect that Gautam was talking about is one experimental realization of a symmetry of nature. And every symmetry of nature should, if it's a non-trivial one. So this is a very concrete problem. Find all the symmetries of nature. And for those of us who've been working in string models and math, you always have this fear that you're working on some system or some model which is going to be inconsistent in some way, and there won't be a consistent answer to the question that you're asking. But this is a question that has to have an answer, because unless you question whether the real world is consistent. Yes, Andrea. I mean nature. By nature, I mean the things that we measure in the world around us. And so, for example, yes, the universe may be de Sitter space, but that does not prevent LIGO from proposing experiments to measure the memory effect. So the cosmological constant is so very small that it's a good approximation to yeah. So by nature, I mean things that we can measure. And the cosmological constant is 0 to a very good approximation, not a perfect approximation, but that doesn't prevent us from measuring these things. Yeah. Well, I've written papers on that too. I have ideas on that, but they didn't get as much traction. There wasn't as much to do with them. We don't. There doesn't seem to be as useful or robust a proposal out for thinking about that. And even if we did understand that, I don't think it will lead to. It's probably true that, or astronomers believe it's true, that in the infinite future there is a boundary which looks like de Sitter space. Maybe it's some weird multiverse thing, but that wouldn't be likely. This is working in the flat space approximation. Not only is more likely, but already has led to new experimental predictions. And Another thing that we'd like to do, more on the theoretical front, is we would like to constrain quantum gravity scattering amplitudes. So there's kind of a lore I think in the old Wilsonian paradigm, if you had asked anybody, 30, 40 years ago, what do quantum gravity scattering amplitudes look like? They would say, well, they could be anything. We have to know all the higher dimension operators, and the more higher energies we probe, the more free parameters are. And unless we know the theory of everything, we're never going to predict them. But now we're beginning to see that that there are already people have understood in a very concrete way in the Amplitudes program and in other places that there are lots of constraints on model independent constraints on, and that's what I mean by bottom up, model independent constraints on what quantum gravity scattering amplitudes can look like. Another one is not unrelated, is to enlarge the swampland. Are there low energy effective field theories that don't obey, that aren't consistent with the many symmetries? So we now know that there are infinitely many more symmetries of nature than we thought there were only 10 years ago. And the symmetries of nature that we knew about certainly related coupling constants. And is there some sense in which the new symmetries also relate coupling constants? Okay, another one is to make, yeah. Enlarging the swampland means that there's more things that are inconsistent. Yeah, that's good. We'd like to rule out everything but one thing. That would be the ultimate goal, right? Yeah, then we'd like to make more experimental predictions. So, of course, one thing that one prediction of these symmetries is the memory effect, which LIGO seems to think they're going to measure in the next 5 years or something. It doesn't seem to be that far out of reach. But I don't think we can really claim that as a, it does follow, and it does become connected with a symmetry within the celestial holography program, but I don't think we can really claim that as prediction of it, because the prediction was made using other methods 40 years ago. But there are other things like the spin memory, the subleading memory effect, which LIGO, in fact, there is a proposal, actually a number of people, it's a growing enterprise within the LIGO collaboration now to try to measure the spin memory effect. And so that is definitely some experimental prediction that came out of this new way of thinking of things. There's also a prediction that who's on that? Adam and Monica and Anna and I made for the future electromagnetic memory, which can be measured at the Future Electron Ion Collider. And also a little bit of a stretch to call that a prediction, because like ordinary memory, you can could have understood it from other ways, but it fits nicely into this framework. But there might be more things like there might be more things like the subleading memory effect that can be seen in that billion-dollar facility. This is something that I think not very many people are thinking about in our community, and probably we're thinking about more, both because it's really fun to talk to experimentalists and make predictions and understand how their detector work, but even more importantly, because when you start talking to them, you start thinking about things in different ways, and you learn new things about the subject. Now, one thing that got me going was, and this is pretty indirect, but of course, understanding black holes. So all of these conservation laws, of course, apply to processes where black holes are formed and evaporate. And so there are infinite number of conservation laws that govern that. And so we'd like to understand how these conservation laws, they enforce correlations between the outgoing Hawking radiation and the quantum state of the black hole. And we'd like to understand exactly how that works. That's the soft hair program. But even more generally than that, it seems unlikely to me that we can understand how a black hole works, like a Schwarzschild black hole, not an ADS black hole, without also understanding flat space holography. They seem like two pieces of the same problem. Certainly, our understanding of black holes with near horizon ADS, in fact, it went the other way around. We understood how the black holes work, and that helped us understand how ADS holography works. So now there's one more goal here, and that is to connect. It's qualitatively different. It's not a bottom-up one, and it's something that I think has become very exciting and interesting in the last year or so, which is to kind of connect, exploit, expand, and interpret results from twistor theory and also what's been called twisted holography. So this is more not so much furthering our understanding of the real world, but understanding and connecting with what has been for the last 40 years, an incredibly beautiful and well-developed program in mathematical physics, twistor theory, and the many, many things. I shouldn't even really be calling what people call twistor theory now is like calling string theory what people call string theory now. It's expanded out into so many different directions, and it's tied in with also the Amplitudes program. And it seems that since especially since the discovery of the W1 plus infinity in the soft algebra, which applies in the classical limit to every minimally coupled theory of gravity, that W1 plus infinity has been recognized is exactly the same W1 plus infinity that Penrose used in the 60s to sort of solve the self-dual Einstein equations in his nonlinear graviton construction. And I think that the information flow in this case, in this connection between the different fields, has wonderfully gone both ways. Usually it goes one way, but in this case, it's really gone, I think, both ways because, well, maybe I'll talk about that a little bit more. Maybe I'll talk about that a little bit in a minute. But you know, when W1 plus infinity was used in the 60s to solve the self-dual Einstein's equations and construct the nonlinear graviton, it wasn't understood that the linearized W1 plus infinity deformations had anything to do with asymptotic symmetries. In fact, the asymptotic symmetries weren't all understood then. Super translations had just been understood, I think, by people just down the hall from the people, but it wasn't understood that these W1 infinity that the twistor people used are actually observable, measurable symmetries of the real world. You probably would get different answers if you asked different people, but I didn't get the impression that it was thought that this W1 plus infinity was a symmetry that even had a place in the real world, but that it was some special thing that it was some special thing that involved to the special integrable models. On the other hand, as I'll talk about in a minute, we didn't, when we first started thinking about celestial holography, it seemed like a very, very distant goal to construct a model, a top-down model, where you could actually have a really precise holographic dual pair. And now there's been a lot of progress. I'll talk about that in a minute. There's a lot of progress on that, and it seems like next time we meet, somebody will have fully nailed that. So it's really a wonderful example of different fields colliding, understanding infrared structure of gravity and self-symmetries, and colliding with twistor theory and amplitudes program. Okay, now I'm just going to talk in a sort of more random way about what looks to me are going to be fun things in the next year. But maybe somebody wants to add something to this list, or ask a question or make a comment. Okay. So so let me make a list now of the things that we are the most precisely confused about, which are the things. There's lots of things we're so confused about we don't even know what to say, but there's some problems within this subject where our confusion has taken a very precise form, which means that it might be ready for some progress. One of them is, as we discussed, soft theorems in quantum field theory are symmetries, and a couple of soft theorems have been proven, recast as symmetries, and then it was found that they didn't commute. And in fact, so therefore you had an infinite number of symmetries. And that's been known for a while, that there are infinite number of soft theorems and therefore an infinite number of symmetries. What's happened in the last little more than a year, it's found that a subset of them, the positive helicity graviton ones in classical limit of minimally coupled gravity form W1 plus infinity. But we don't expect, well, I don't really know what to expect, but I guess it's still going to surprise me if there's some sense in which W1 plus infinity is an exact symmetry of nature. And in fact, it has a known deformation, which is called capital W1 plus infinity, which is a much more complicated symmetry algebra. But I'm not even sure I think that that's exactly what we're going to get when we study these deformations. And where do the deformations come from? Well, they come from quantum effects, though the way that quantum effects can deform this symmetry algebra seems to be extremely limited. In the case of gravity, it can't, these things are labeled. They're sort of, the generators are written W1, W3 halves, W2, W5 halves. And in the case of gravity, the first three of them are protected. But nevertheless, we expect that that there's going to be, well, it seems likely to me that there's going to be some more deformations eventually. So there's deformations from quantum effects. There's deformations from higher dimension operators, a short list of them. Not any higher dimension operators. It's like an anomaly kind of thing where there's only a few operators that can deform the algebra. And then there's, I don't know if you would call it so much a deformation as an enlargement. It depends on what happens here from the other chirality. So this is just one chirality. The soft theorems associated with, say, positive chirality of soft gravitons. And there's a similar story for gauge theory. So this seems like a really mathematically well-defined problem that we can sink our teeth into and make progress on. And I'd like to mention that I think that there's some exciting work. I don't quite know how to put it together, but there's some exciting work being done as we speak by the Brown group, which I guess includes Adam now, since he moved there. And in showing that something that looks like a violation of associativity in some of the commutators. I'm not going to say any more because I'm sure I'll say something wrong if I say any more words about it. But I don't know how the story is going to resolve itself with these violations of associativity. The most dramatic thing that could happen, but I wouldn't bet on this being the outcome, is that everything that violates this associativity is in the swampland, which would give us a sort of, that would make some experimental predictions, and that would give us, sort of an unprecedented, reflection of quantum gravitational physics into low energy observables. It might be something like the kind of thing Dan has been talking about, where these generators should really be viewed as things which are moving you not exactly on a group manifold, but on the tangent space of some curved manifold, and the associator should more properly be interpreted as the fact that the space of vacuum manifold, different W infinity vacua, is a curved space. That's another possibility. I don't know how it's going to work out, but it seems like a very sharply posed question, which I think is central to the field, and I'm optimistic that it'll be on its way to a solution by our next time we have a meeting. Now, another thing that looks really exciting, also exciting, I can't keep repeating this word, but why not? Okay, exciting. There's been a lot of progress, as I was alluding to a moment ago, using ideas from ideas from all over the place, really. Some of them from twistor space. There's the group at Northeastern, including Angelos and Tom Taylor and Binju and Fan, and there are other collaborators that have gotten very, very close to constructing an exact dual pair, where on one side you have a two-dimensional celestial conformal field theory, and on the other side you have some four-dimensional space-time scattering theory. Now, what there is now, you might have think there already was that, but that's not quite there yet. What there is now are things like, there's the Northeastern group, there's also Kevin Costello and Natalie Paquette and Atul, and Tim's been involved in this, and Lionel, and using twistor theory techniques, and starting with BF, with completely well-defined BF theories in twistor space, and reducing them down to 4 dimensions, and finding the chiral algebra in there, and relating it to the celestial dual. Now, the kind of statement that has been made so far is, let's take this one space-time theory, 4-dimensional space-time theory, and compute the scattering of soft gluons or soft gravitons in this space-time theory, and that is equivalent to scattering of some current algebra in a 2-dimensional theory. Oh, and I also should add, there's a group at Harvard, myself and Shruti and Walker and Eduardo, who have also made this kind of statement. And so it's a piece of a bulk theory equaling a piece of a boundary theory. We want to do better. We want to have like what we have in ADS-CFT. Here's a bulk theory, has some complete set of observables, whatever you mean by complete. If it's in the case of celestial holography, complete would usually mean some set of states and a unitary S matrix, and some complete set of states that comprised a unitary S matrix. And then on the CFT side, it would mean something like, but it gets tricky because these CFTs aren't unitary, we don't expect. It would be something like, here's a spectrum, a set of operators, all the dimensions of the primaries. Here's their operator product expansion. The operator product expansion closes, and the 4-point function factorizes on conformal blocks that involve all the operators and only those operators. That would be one way of phrasing it. That level of completeness, we do have complete statements like that in ADS-CFT, but we don't have that level of completeness. And this exercise is important for two reasons. It's important because it's good to work from the top down, and it's good to work from the bottom up. And if you're working from the bottom up and you have some examples from the top down, they can guide you and give you hints about what you might expect to see. Okay, the other thing that I hope is coming is, so far I've hardly said the word string theory. And all of this was sort of secretly motivated by string theory. There's lots of ideas in here that are familiar, have a familiar ring to them in string theory. One of the facts that I'm kind of obsessed with is that the foundation, the starting point of string theory, the Veneziano amplitude, was to find a scattering amplitude which had the property that you could get the full amplitude by either summing over the S channel or the T channel. Not summing over the S channel and the T channel, S or T. And quantum field theory is different, usually, because Feynman diagrams, we add the S channel diagrams to the T channel diagrams, and we get some expression. And we now know through lots of work in the Amplitudes program that Feynman diagrams, as universal and beautiful as they are very redundant, and they're more efficient ways of writing things. So one of the things that we see without even doing any work is that in celestial holography, if you have a 4-point function, you can, of course, compute it using the Feynman diagrams. But if you use the celestial dual, you have a celestial conformal field theory, and it's a correlation function of celestial conformal field theory. And if that obeys the, so it's formally true, but a long way, it's formally true, but a long way from having been explicitly demonstrated, that you can take that 4-point conformal field theory correlator in the celestial conformal field theory and expand it in the S channel or expand it in the T channel. That's crossing symmetry. So it's S or T, not S and T, which sounds just like string theory. So already just the assumption that you have a complete quantum theory of gravity leads you to, without saying string theory, leads you to this S or T, which was the starting point of string theory. So one of my hopes, and there's lore might be too strong a word, there's a conjecture that string theory scattering amplitudes are, under some conditions, the only consistent string theory scattering amplitudes, or things like them, are the only kind of scattering amplitudes that you can have in quantum gravity. And maybe statements like that, we could hope to prove them with using all these new symmetries that we've learned about. And that is part of what I had in mind when I said constraining quantum gravity scattering amplitudes. But even more than that, in celestial conformal field theory, you have a correlation function in a two-dimensional conformal field theory that gives you a space-time S-matrix element. We've seen that before in chapter 1 of Polszyński's book on string theory. You take a world sheet of the string, you compute some correlation function, and that turns into a space-time scattering amplitude. So it feels as if there should be some more precise connection between the celestial holography program and fundamental string theory. A few comments about this have been made. One that I like very much by Stieberger and Taylor a long time ago, that if you go to large conformal weights, the string theory, that's large space-time conformal weights, large boost weights. The string world sheet gets pinned to the celestial sphere, and the string world sheet is the celestial conformal field theory in that limit. But we'd like to understand it in a more general way. And finally, I keep harping on this. I guess it would be good to see more ideas for how we could talk about more experiments that measured these symmetries. So I guess I'll stop there, and I'll take any questions or comments. Getting flat space out of what? Yeah, so here or here? Yeah, I think it belongs on the left. Getting flat space from ADS-CFT. And I don't understand why. Of course, it works beautifully in 2+1 dimensions. This seems to be devilishly hard. Even simple things like seeing how the soft theorems arise in the flat space limit of ADS-CFT seems to be devilishly hard. And indeed, one would like to see some sort of derivation of some celestial holography from ADS holography. It's not like DS-CFT. You can't really hope to get de Sitter space as a limit of anti-de Sitter space. But I agree, flat space, yeah. Yeah. People are understanding more about that, and that could be coming too, yeah. Yeah. Yeah, okay. I mean, I don't want to like overplay this, but it could happen that yeah, it could happen that you know, certainly the equivalence principle, the leading soft graviton theorem. This is another way of restating what was in the Brown paper. But I don't know if this is the right way to think about it. The leading soft graviton theorem just tells you that gives you a relationship between the coupling of 3 gravitons and the coupling of 2 scalars and a graviton. It just tells you that that the graviton couples to the scalar stress tensor. There isn't a freedom there. And so that comes from the leading, can be thought of as coming from the leading soft graviton theorem. But now we have more subleading theorems, and they could give us relationship between coupling constants. And there might also be signs of coupling. Yeah.
Thank Andy for a great opening. Thank you, Rob, and you've been very close to back. Yeah,